Okay, I'll start. The most important thing I'm going to say, and if anyone comes late, I shall come back to this slide so they get it, is you don't do this. Under no circumstances are you to code up anything I described today in this lecture. The reason is there exists some excellent packages, and they're free packages, so there's no excuse. They're excellent and free. They're excellent because they're professionally written. That means they're safe. So if they go wrong, or rather if you ask them a wrong question, they'll tell you your question is wrong. And they even give a suggestion about where you're going wrong. Where if you hand code this, you won't put in those safety nets. They're also faster than you can hand code, because they call subroutines, which call subroutines, and eventually they use information about the structure of your CPU, about how you can cache things. Okay, so I'm telling you, you mustn't code any of this. So why am I talking at all? Well, it is because you might like to know what's available. There are many different linear problems, and there are different routines that deal more appropriately to different types of problems. So this is a survey of the methods that are available, and you may be able to see that some are better than others for different situations. It's only a very brief review, even if it is just over an hour long. There are many books, many books, with a minimum size of 200 pages, and that go into much greater detail. And so obviously there's a lot more there than I can describe in a short time. Okay, so we'll start. This is about linear algebra, and we all know that the fluid equations are nonlinear. So why is there any room to talk about a linear problem? Well, by now you know that there's an unavoidable Poisson problem. And Poisson problems are linear problems and big problems, so we want to know better ways of tackling them. There's also something very important, that when you get a steady solution for a flow, you might be interested in its stability, nearly always the linear stability theory, and so you're back into a linear question. So there are linear problems in nonlinear fluid mechanics. And there's essentially two problems. There's the matrix inversion problem, solving AX equals B, where A is a matrix and X and B are vectors. And there's a great variety of matrices. They can be dense or sparse. Sparse means that 90% of the elements of the matrix are zero. And you might be faster if you use that information. And then the matrices might be symmetric matrices. They may be positive definite. They may be banded. There's a whole range of different features, and if you exploit those features, you get a faster code. Okay, so that's one type of problem with our matrix inversions and with different types of matrices. And then the other problem is the eigenvalue problem. For stability, you want to know the growth rates. And there's the eigenvalue. So this is a matrix operating on an eigenvector, results in if you operate the matrix on a vector and it turns out to be a vector in the same direction, it's called an eigenvector, and the size has been increased by an amount called the eigenvalue. So this lecture has two halves. We'll deal with the matrix inversion by three methods. One is by Gaussian elimination. One is by QR, just converting the matrix A into QR form, which is a rotation times an upper triangular. And there are, in fact, three methods for doing that. And then there's conjugate gradients for sparse matrices. And then in the eigenvalues, again, there are three methods. There's the power method, which gets you the biggest one quickly. And then for small systems, there's a Jacobi method. And then we can try and get there's the main method, which is much more complicated. There's some late arrivals. Late arrivals, you must at this instant read the red phrase. Don't ever code this. And other people explain why. Okay, so one of the free packages, which is quite good and extensive, is LARPAC. They're free, you can download the library. There's a very nice, because there are so many routines available, there's a search engine for you to find out on its website which routine you would like to use. So this is for solving version of the question AX equals B, the matrix inversion problem, is to do a least squared fit of the AX minus B is reduced to its smallest amount. There's also issues called singular value decomposition. And there are generalized eigenvalue problems, which are AE is equal to lambda times, not E, but BE. So there are two matrices involved. It's a generalized eigenvalue problem. Okay, so the search engine will ask you what question, what you're trying to solve, and then how accurate do you want to be? Is it single precision or double precision or more? Is it real or complex variables? The matrix, is it symmetric? Is it symmetric positive definite? Is it banded? Or is it sparse? And what is the packing system? And the search engine will tell you which routine, like this one here, SGESV, which I'll explain in a minute. And this routine calls the numerical routines, which call the little things that do the arithmetic routines. And you don't have to know about that, you just have to know about the top level and have downloaded the library. So for an example, if you have real numbers and single precision, you need to have green S at the beginning. If you are solving a general matrix, there's no special property of the matrix, you want GE for general matrix. And then if you're solving linear equations at AX equals B, you want to have SV. And there are varieties of that. Okay, there are different letters that correspond to doing different. And then the argument is, first one is n, which is, the matrix A is an n by n matrix. And you can see the matrix as number 3 along the list. And this routine actually doesn't just solve AX equals B, it will solve AX equals B1, and then you can give it another vector B2, another vector B3, another vector B4. And we can stack those B's into a B matrix, and you have to tell it how many right-hand sides, how many B's do you want to use. That's N, R, H, S. And on the whole, you set A equal to LDA and LDB equal to B. IPV is the pivot permutation matrix, which you won't understand from it. And info, the last thing, is a flag, and if it comes back negative, it's failed, because you've asked it to invert a singular matrix. No. Something's gone wrong if it's negative. If it's 0, you're okay. If it's 1, 2, 3, it's gone wrong at lines 1, 2, 3. So it's working through. So there's information you have to test. Okay, so that's an example of these free libraries available. So what do you do to solve these matrices? This linear system of X times A equals B. You take the first line and you divide the first line by A11. So the coefficient of X1 now on the first line becomes 1. So you divide the whole line. That doesn't change the solution at all. And then you subtract multiples of the first line. You subtract from the second line. Now that this is 1, you subtract A21 times the first line all the way along. So if one equation is true and another equation is true, linear multiples of those equations are true. So okay. So the result of subtracting A12 of the times the first line from the second line is, of course, to turn this into 0. And there are non-zero all the way along. And then you repeat that for the third row, the fourth row, all the way down to the bottom of the nth row. When you've done that, you've got 1 as a coefficient here, 0 for these coefficients, and then you've got a smaller matrix. Then you consider the smaller n-1, n-1, and proceed in the same way. You take this coefficient and you divide this equation here by a22. You're dividing 0 by a22 won't change it, 0. So you divide this and that will become 1. And then you subtract multiples of these equations down here, whatever the coefficient is here, times that row from this row. Okay, so hopefully you've seen all that. And you end up with a matrix which is 0's coefficients under the diagonal, 1 along the diagonal, and then non-zero, well, other things up there. So then if you stand on your head, you can start at the bottom, where actually this is 1 times the xn is equal to bn. We can all solve that. We can then substitute that, go to the next row up, where there's an an minus 1. Of course, that's 1 times xn. We don't know xn minus 1, but we know xn, so we can put that x in there and find this. So you back substitute all the way up to the top and then find all your x's. So just a rephrasing of all of that is called LU decomposition. That is to write the matrix A is equal to L times U. And L is lower triangular and U is upper triangular. And in fact, we'll arrange for the lower triangular to be 1 along the diagonal and non-zero down here, but 0 is above the diagonal, that's lower. And then the upper one, we can't have 1s. It's going to be 0 below the diagonal. So we'd like to write the problem like that, and it's done in the same way that you go down row by row. So K is going down the rows, and you set the upper triangular essentially equal to the row that you've arrived at. So you copy the kth row into the upper, and it will, by the time you arrive there, have zeros all the way at the beginning and non-zeros afterwards. You then, for the lower part here, you put the whatever the coefficient is when you arrive, divided by the coefficient of AKK. That was dividing all of the rows by something. That was when you were subtracting multiples of all of the row. And then you have to subtract off all those rows to get the A's. So this is, the upper one is the equation when you arrive at that row. And the lower triangles are the multiples you use for doing the subtractions. So the number of calculations you have to do is 1/3 of n cubed for an n by n matrix. However, if the matrix happens to be tri-diagonal, then in fact you only have non-zero 1 below the diagonal. You only have non-zero on the diagonal and 1 above the diagonal. They remain tri-diagonal matrix. And if you know you're going to have lots of zeros everywhere because there's only non-zeros next to the diagonal, why try and calculate them according to this? And that would reduce the number of calculations you do very considerably. Okay, the way you solve AX equals B, now you've got A as LU, is you first solve LY equals B, and that is this back substitution system. Sorry, this is the downward run. And then because Y is UX, you can then solve the upper triangular problem, which is the back substitution run. Okay, actually finding LU, L and U, is n cubed operations. But this is why, but very often you have the matrix A is static, but you have different B's as you time step through the calculation. Each time step has a different B, but the A remains constant. So if you store A, you store L and U. This solving for the x that satisfies LU, x equals b, is a mere n squared calculations. And it's slightly more, effectively I've got the inverse of A, but it's better than, it's more efficient than having the inverse of A. Okay, something can go wrong in this calculation is as we go down, the diagonal when we arrive on a row might just happen to be 0 or numerically very near to 0. You can't divide by 0, you can divide by a number which is numerically very near to 0, but it's bad for you. So there's a system of pivoting, which is, we have an equation and then another equation lower down. The order of the equation doesn't affect the answer. So we can rearrange the orders of the equations. So what we do is, if we arrive at one point, we look at down below it, is there a bigger coefficient there? There's all zeros out here. And we look down, is there a bigger one? So if there's a bigger one, we switch those two rows round. Then we're dividing by a nice big number, the biggest we can find. So that's called row pivoting. And it is actually possible to do total pivoting. You can actually change the order of the equations. Instead of having a x1 plus x2 plus x3, why not switch x1 and x3 around? It doesn't change, so switching the columns. It's remarkably confusing, but you can do it. And that's called total pivoting. And on the whole, it's not worth the effort. Okay, so we won't talk about it. But for row pivoting, we don't, with a very, very big matrix, we don't actually copy one row to the side, then copy this row down to it, and then pick this one up and put it back in, because there's a lot of work to do. So what you'd have is you have a little matrix that stores which pivoting. So if you ever want to address row 4, it looks up in the pivot table and says, aha, no, I swapped it for row 10. Please go to 10. So you have a pivot table. So that saves interfering with the original matrix. Okay, a very important thing is when we have A equals LU, we can now work out the determinant of A very quickly. The determinant of A will be the determinant of L times the determinant of U. The determinant of L is actually just the product of all the ones, because otherwise you involve a 0. The determinant of U is just the product of the diagonals of U. So once you've formed LU, that's n cubed operations, finding the determinant is just n multiplies. Forming the determinant of A according to the way you're taught first at high school is factorial n terms. You just don't ever want to do what you were taught. That was the most stupid thing they ever taught you, right? It's okay by a 2 by 2 matrix, but it's even quite a work at 3 by 3. Okay, if the matrix happens to be symmetric, then it turns out that U is a diagonal times the transpose of L. And if the matrix is symmetric and positive definite, it guarantees the diagonal terms are positive, so I can take the square root of them, and I can put a square root on one and a square root on the other, so I can say A is one matrix times a transpose, and both of them are triangular matrices. If the matrix is tridiagonal, then both L and U are tridiagonal, but of course they're guaranteed to have zeros above and below the triangle. So they're actually just two lines. Okay, errors. There's always an error. There's at least the rounding error in the calculation. So if there is a little error in B, a rounding error in B, because it's real numbers on a finite arithmetic computer, then when you solve AX equals B, you could be in the worst situation dividing by the smallest eigenvalue of the matrix. So the error will get amplified by dividing by the smallest matrix. And it could well be, could also, in the worst situation, be that B, when you're solving AX equals B, X has B divided by the biggest eigenvalue. It gets reduced a lot. So the error gets reduced, even blown up by dividing by the smallest eigenvalue, where the solution gets increased a lot by decreased a lot. So the gap between the error and the solution, the relative error, has increased by the ratio of the eigenvalues, the biggest and the, which is called the condition number of the matrix. And unfortunately, in large partial differential equation systems, the condition number could be 10 to the 4, 10 to the 8. So what was a negligible rounding error, theoretically, can be blown up enormously. So that's sort of unavoidable. It doesn't tend to happen, but it could. In LU decomposition, or Gaussian elimination, it tends to be the errors get, because you're repeating line after line, you can sort of double the error every row that you process, so that the error could increase by, for another reason, by 2 to the n. So you're stretching the error. And so there's an alternative, which is called QR decomposition. Q is a rotation matrix, so we're rotating the error, that doesn't stretch it. So this is considered better for us, if we rotate the error with a Q rather than LU decomposition. It's much more complicated, but it's good for you. It's also useful in finding eigenvalues. You have to be able to do a QR decomposition. So R is going to be an upper triangular matrix again, and Q is a rotation, well, it's an orthogonal matrix. It's a rotation or a reflection, and it has the property that Q times the transpose of Q is the identity. In other words, the columns, and equally the rows, are orthogonal to one another. And moreover, they're not just orthogonal. If you form the scalar product of one row, its size is 1. Okay. This says that you don't stretch the errors. We use it for eigenvalues. The determinant of a rotation matrix is 1 still. So the determinant of A is just the determinant of R. There are lots of Qs. It's not unique. And I'm going to quickly describe 3 methods: Gram-Schmidt, Givens, and Householder. So Gram-Schmidt. You write the matrix as n column vectors. So these are column vectors 1, 2, up to n. You grab hold of the first column and you call it Q. This is about to become the first column of the matrix, of the rotation matrix Q. That's why it's Q. But of course it's not size 1. So we go and make sure it's size 1. So this now is actually the first column normalized is going to be the first column of Q. Then we go to the second column of A, and we want it to be orthogonal to the first column. So we start with our first attempt at Q, second column of Q, as being the second column of A, but we have to remove any component in the direction of the first column, and then we have to normalize it. Then we go to the third column, which is going to be the third column of A, is going to be the third column of Q, and we remove components in the direction of the first column and the second column, and we normalize it, etc. So that's Gram-Schmidt. In big matrices, what I've told you is unstable. So there's a trick that once you've got Q1, you immediately go down all the other columns and strip off the components in the direction of Q1. So we don't do it in this order. Once I've got Q1, I take its components out of the remaining columns of A. And that way around it's stable. But anyway, you're not coding it, so it doesn't matter. You understand the principle. And then, out of this calculation here, we can dig out what is R. The diagonal elements of the QR, diagonal elements of R are in fact these normalizations. And the off-diagonal terms are these projection coefficients. Because if you look at this last equation here, it is saying A3 is equal to this, Q1, this, and then that, put in there. And therefore, the R's are just that. So that's one method of getting A as QR. The next method is called rotations. So we're in n dimension, a very large number, but we do a rotation. You don't do, okay. To do a rotation in the 1-2 plane, you rotate about the third axis. That idea is only available in 3 dimensions. In higher dimensions, you rotate in the 1-2 plane. So I'm going to rotate in the IJ plane. It's a standard rotation matrix in the IJ plane. And I choose how far to rotate in order to eliminate one of the elements of A. So we're trying to, by doing a rotation of A, I'm trying to find R, the upper triangular matrix. So I'm trying to zero the under-diagonal terms of the emerging R. And I have to do rotate all possible IJ rotations to do this. So you choose the theta, so it actually eliminates the GIJ, the AIJ, that you have a provisional R, to eliminate the IJ, lower term. So it's probably the AJI. I don't know, I can work that one out. You need a strategy of how to when you rotate this, you zero one term, but you may turn a previous zero into a non-zero term. So there is a campaign to work through this matrix so that you introduce zeros without undoing. And what you do is, in fact, is you start at the 1, 2, and you work down the first column, making zeros. Then you move to the next column and work down, etc., etc. So there's a strategy for getting through it. Okay, the last one is more complicated. And it's called householder. And it represents, Q is R, in fact, is a product of reflections. So this happens to be a reflection. H is a vector. It may not be a unit vector. And I have to persuade you that 1 minus HHT on H squared times X, which is actually equal to X minus H dot X divided by the size of H squared, is a reflection. So if X is, and there's a 2, thank you very much. Right, so if X is perpendicular to H, that's 0, and the operation of H on X is to give you back X. On the other hand, if X is in the direction of H, this is just HX. This is the direction of X, so X divided, normalized. So we end up with X minus 2X. So minus X. So this is a reflection in the direction of X. In the plane, but it's the hyperplane, the n minus 1 dimensional plane, perpendicular to H. Okay, you'll never see how this works. You take there's going to be n reflections. For the first one, you need H1 for the reflection 1. You take a vector which is in the column, the direction of the column of A, and you add just a little bit to it. You add in the top row of column 1, you add a coefficient which is in fact the size of the length of the vector times the sine of A1. If you take the sine of A1, 1, then this increases it. There's just a slight danger that if you just casually add the size of the length of the vector and this was negative, then you end up with 0. Okay, then you go away and do some algebra and decide that H product with the first column A is equal to something, and H product with itself is 2, then you can go over to this expression and check that it truly is a reflection. And if you operate H on the vector 1, A1, you end up coming back with minus alpha 1 and 0 in all the other directions. So this H operated on the matrix A puts zeros down the first column, other than the top term. So I've produced something and then zeros underneath. We then think about the n minus 1, n minus 1 bit that's left and produce H2 that operates down there with 0 at the top. And then it's a product of them. Okay, and very important advantage of this method is that whenever you want to form Hx, this is not an n by n matrix operating on x. It is exactly that expression. So this is n calculations rather than n squared calculations. So reflections are cheap to evaluate. Okay, so that's Gaussian elimination, which is LU decomposition, and QR, which we'll need for eigenvectors, is for what's called directly solving the problem, to exactly solving the problem. When you get to very large sparse matrices, we don't try to exactly find the solution. We iterate, like successive over relaxation, we iterate down until we've got to near enough the answer. And that's much cheaper. And there are faster things than successive over relaxation. So there's a little example there that if you have an n by n grid, and the Poisson problem for an n by n grid is to have n squared unknowns. So the A matrix for AX equals B is going to be n squared by n squared. So that's n to the 4th elements in the matrix A. But we know it's sparse, that nearly all the elements are 0, because we know there's only, if you look at the little numerical model, there's just 5 n squared unknown, non-zero terms. There's a big difference between n to the 4th elements and 5n squared non-zero elements. So we want to exploit that. Okay, the iterative method in general is to say A is equal to B plus C. You have to choose B and split the B and C carefully, and then you can take the C onto the other side. So we've got AX is equal to BX plus CX equal to little b, and then we say, well, we'll take, for the next one, the previous iteration is equal to B. We take that onto the other side, and we just have to invert B. So, right, so you want to choose B that you can invert cheaply. So this B is something we can invert cheaply, and you'd also need the size of B minus 1C to be less than 1, otherwise this iteration process won't converge. So you can look, the experts in the field look at Gauss-Seidel and SOR successive over relaxation. What are the BC split matrices? And they can prove that B minus 1C is of size less than 1. And the difficulty is it is equal to 1 minus 1 upon n, or 1 upon n squared. It's only just under 1, which means you need lots of iterations. So for Gauss-Seidel, it's 1 minus something over n squared, which means you need n squared iterations to get anywhere. For successive over relaxation, it's 1 minus something over n, so you need n iterations. Right, and then conjugate gradients. This is a jolly good method. It's for general AX equals B. If it's a Poisson problem, very often there's an even better method. But for just solving AX equals B, when A is sparse, and it has to be that A is symmetric and positive definite. So if you were to diagonalize it, the diagonal elements, the eigenvalues, are all positive. Right. So to solve Ax equals B, we essentially form Ax minus B squared. We're going to try and minimize Ax minus B squared. But it's not quite that. There's an A inverse sitting in the middle. So there's a way of measuring the size of Ax. We emphasize it by the size of A. And if we multiply that out, there's a quadratic term in X, there's a linear term in X, and then there's a constant term in our quadratic in X. We try to minimize that. We need to know what is the gradient of F. So direction that F decreases fastest, and that just happens to be Ax minus B, which is the residual in the calculation. So if we're in our iterative process at some solution xn, and we have a direction u that we'd like to go along in order to minimize this quadratic form. How far do you want to go along the direction u to minimize this quadratic form? You want to go distance alpha. So you substitute x plus alpha u, xn plus alpha u, into this expression, and obviously you get, when alpha is 0 f at xn, there's a linear term, obviously, which is the gradient, and then there's a quadratic term in alpha squared. That's just a scalar in alpha quadratic, so you can find the minimum, and the minimum is at getting more complicated expression here. Remember, the gradient of Fn is the residual at stage n. So we can go along that distance and get, in our process of minimizing F. Now the question is, how do you choose the next direction? If we knew how you can randomly choose the first direction, how do you choose the next direction? And many people say, because you've been looking at other areas, go down the steepest descent. And that turns out to be wrong. Because in a high-dimensional system, very typically, the geometry of this quadratic is in this direction. No, let's do it. In this direction is very steep. So the quadratic is a parabola that's very steep. In this direction, which isn't perpendicular, it's a rather gentle quadratic. If you have minimized, where were we? This way, wasn't it? Right, very steep, and you didn't quite get to the bottom because of some error, and you now ask what is the direction of steepest descent. It's in the same direction because you spend ages rattling around this steep-sided parabola. So you need to invent a new direction which introduces new information. And that's the conjugate direction. Okay? So that's the idea. That's why you shouldn't be steepest. So they're saying you rattle around the steepest and don't move along the valley. So we now think we've moved in the direction u and found the minimum. Now we're going to have a new direction v. Let's see what had happened if we started at xn, move alpha, which we know about, in the direction of u, and now we introduce a new direction v, which we don't know yet, and move a distance beta. What would happen? Well, we get a quadratic in alpha and beta. And so there's the function at xn, the linear term in alpha, the quadratic term in alpha, which we've been thinking about. There's also a quadratic term in beta and a linear term in beta, and there's a cross term. And if you don't want to minimize f, having done it in alpha, and you don't want your next direction to interact with the alpha, the u direction, you choose that that is 0. The cross term is 0. So you do something genuinely new with beta, with v. So the conjugate direction is such that u dot av is 0. This is the routine. Very complicated. You start somewhere at x naught and u naught. And then there's at any stage there's a residual, which is axn minus b, which is the gradient at the current time. and then it's this iteration. So we first know how to work out alpha, so the distance you've got to go in the direction of u to get the minimum. So that's the thing we've just calculated. So you make that move and go to the new point, which is alpha along the direction of un. You work out the new residual at this point, which just happens to be the old residual times alpha times au. And then you choose the new direction as being this new residual and beta times un. We want to find the component of in the direction of u that gets us this conjugate condition. So we adjust our possible direction v. We remove any bit in the direction of u that makes sure that's true, which is the calculation here. It turns out the answer's here. Okay, the rather nice thing is that each step in this iteration, you have to know a times un for 3 applications, but you need only calculate a un once. And then when A is a sparse matrix, working out A times a vector is just an end. You just visit the non-zero locations. So that's rather cheap. So it's very nice not to look at the matrix A. We probably never write down a sparse matrix. We just write down for the matrix A when it's sparse, how to work out the matrix operating on a vector. So I just walk through my grid, applying the numerical molecule to the vector, the new vector u. Yeah. Okay. You can actually show there are alternative pretty forms for alpha and beta, and you can show that if un plus 1 is conjugate to un, is also conjugate to un minus 1, un minus 2, all the previous ones. As you're never going to code this, you don't want to know that necessarily, but it's rather pretty, right? Finally, we'd like to solve ax equals b. I can multiply by b inverse. Well, I can multiply by anything. A preconditioner, P. The solution X is the same. So there's a game. Can you find a nice matrix P that makes this simpler? So you want a matrix P which I can invert fairly cheaply and doesn't corrupt the sparseness of A. There is a penalty if you multiply by nearly anything P on A, and A is a sparse matrix. It won't be quite as sparse as before, but you try and ensure it doesn't spread it too much. Okay, so that's preconditioning the problem, and it's often, there's something called incomplete LU decomposition. The conjugate gradients really required it to be a symmetric positive definite matrix, and I needed its inverse. Well, in my mind I needed its inverse. I didn't actually ever need its inverse. When the matrix A is not symmetric, you have big problems, and there's something called GM-res, which minimizes, I had A inverse in here, but it minimizes the residual squared. Unfortunately, the condition number of this new quadratic is the square of the condition number of the matrix A. Before I'd inserted an A inverse here, which made sure that the problem still had a condition number of K. So GM-res has big problems. You need more iterations, and eventually it gets stuck. You have to store, for this you have to store all your previous directions, which you don't for a symmetric matrix, and you end up, all these new vectors tend to be parallel to one another and things are not working. So you then throw everything away and restart the problem. So GM res n means after 10 new directions, give up and start afresh with a random start. Eigenvalue problems. Finding the eigenvalue lambda for, in the first case, there's this generalized eigenvalue problem where there's a second matrix B on the right-hand side. There is no finite method. That's not true. You can solve quartics. You can solve quadratics easily. School kids can do that. Some people know how to solve cubics. I don't. And in fact, you can solve quartics. But beyond that, there is no way of solving the quintic polynomial in an organized, direct manner in finite number of moves. Therefore, this is solving a polynomial equation. And in general, there is no direct method, so you have to iterate. If the matrix is real and symmetric, the eigenvectors are orthogonal to one another, and that's all very nice for you and has an impact on the system. If the matrix is not symmetric, it's not nice. There are possibilities of degeneracies. You know, if you've got a matrix which is not symmetric, you can have a matrix 2, 2, 2, and then you can have a number here. When everything else is 0, you just can't get rid of that 3. You can't diagonalize the matrix. There's that degeneracy. And this is just an aside, nothing to do. That in this 2 by 2 system, xy dot is equal to a matrix operating on xy. If you have an initial conditions of 1, 0 and 1, this solution has, for x, this is a solution. And suppose this k, this off-diagonal term, was large. This is decay, with k positive. This is a big decay. So you'd expect the solution to decay, and jolly well it does, but it turns out at time 1, it's very large. It's k large rather than starting at 1. So this is something that happens in these non-symmetric matrices. It's very important in fluid mechanics because U dot grad U is effectively a non-symmetric matrix, and it leads to what are called non-normal modes. So the mode will decay. If you do linear stability analysis, the modes decay eventually, exponentially, but in the short term, they can grow enormously, and they could grow out of the linear regime. So this is a very important feature of linear stability of shear flows in fluid mechanics. Okay, so that's a danger of non-symmetric matrices. I'm going to talk about symmetric matrices. There's a lovely little trick called the power method. And it will get you the biggest eigenvalue quickly. So what you do is you take A times X, and then another A times, and then you keep going. You just apply A several times to a random X naught, so you get AN times X naught. And what happens is the largest eigenvalue wins. If you apply A several times, you get the largest eigenvalue to the power n times the component you had in the direction of the largest eigenvector. So eventually, this matrix, if you have an times a random x naught, you end up looking in the direction of the eigenvector of the largest eigenvalue. And if you apply A times that, you'll find the eigenvalue. So, and a good approximation to the eigenvalue will be A times a power of x divided by its size, to find the size. And a good approximation to the eigenvalue will be this direction. Now, you have an approximation, moderate. You could consider the matrix A minus this approximate eigenvalue times I. Now, the largest the eigenvalue in this direction of A minus lambda I is going to be the true eigenvalue minus the approximate one. So if I invert it, I have an eigenvalue of this inverse matrix, which is 1 divided by the correct lambda minus the approximate one. That's an enormous eigenvalue. So if I now play this trick of iterating a couple of times, this enormous eigenvalue will dominate, and I'll get the new eigenvector to high accuracy very quickly. Okay? That's the way of getting the biggest eigenvalue. There are hiccups if there are two eigenvectors with the largest eigenvalue. You'll get one of the eigenvectors, and then looking for the other one is difficult. And there are tricks of doing, roughly corresponding to this, of doing shifts by an amount of mu, so you could home in on an eigenvalue near mu. The Jacobi is only good for small n by n matrices, small n's. And what you do is, you look at your A, it's symmetric, you find the largest off-diagonal term, and you do a Givens rotation to make sure that that largest off-diagonal term is zeroed. Agreed, you will create non-zeros elsewhere, but you can prove a little theorem that the sum of the off-diagonals decreases by, I think it's 2 aij squared. So the sum of the off-diagonals will go down. Then you've got a new matrix, and you find the largest off-diagonal term, and you apply the appropriate Givens rotation to push down the off-diagonal term. The important thing is that the eigenvalue, if you have this Givens rotation and you apply the transpose post A, that this is still a symmetric matrix, and it has the same eigenvalues as the original. This has the same eigenvalues as the original one, because the eigenvalues of, when you form the determinant of the rotations are 1. Okay, so eventually this converges to a diagonal matrix, and the diagonals are the eigenvalues. So this is the main method. This is what you do in general. Well, sorry, you do not do this. The packages do this for you. Okay, it's 2 steps. What you're aiming to do is to produce what's called an Hessenberg matrix, which is an upper triangular matrix with one non-zero line just under the diagonals. So it's not quite upper triangular. And so that's what it says. Okay. So you consider some q, a times q, a squared times q. Q's a sort of random start for this. So we get all these series of vectors, and we play with them, we normalize them. So there's a sequence of steps where you take the current AQ, at this kth step you take A times the k. You take the kth one along here and apply yet another A to it, and then you go down all preceding terms, finding the components in the direction of the previous Q's that you've got, and then you project out from this V all the previous components, and then you define the first term under the diagonal as being the size of this vector that you've got, and the next Q as being this V normalized. Okay, so the original V that we started here is essentially this definition here, which is this sum of these projections that we've just worked out. And therefore, you can see that this V is essentially A times a sequence of Q's. In other words, I'm saying that AQ is equal to QH using these Q's. In other words, H is Q transpose AQ, and so this produces in n squared operations, if it's a dense matrix, it produces, does it n? It might be n cubed cost, an upper Hessian matrix. And then there's some nice features that if A is symmetric, it has to be symmetric to do this. H is symmetric, and therefore H is a tridiagonal matrix. I was thinking of producing H as being this upper diagonal with an extra one subdiagonal term line, but now I've declared A is symmetric. It turns out that it's tridiagonal. And so when I've said before, you run all the way along the row, you don't have to run all the way along the row because you know lots of things are going to end up as 0. Okay, so we end up with this H Hessenberg matrix, and then what we do is a QR decomposition of it, and then we form a new matrix, which instead of being QR is RQ. In other words, it's Q transpose AQ, and therefore the eigenvalues of H prime are the same as the eigenvalues of A. And so if it was, I think that should be an H. We could produce a new H by this Q rotation, and we found the Q by doing a QR decomposition. It remains Hessenberg, which means if it's tridiagonal, it remains tridiagonal. And the off-diagonal terms have all gone down by this ratio of the dividing by the largest eigenvalue. So it converges miraculously. If you repeatedly do a QR decomposition and restructure, find a new H prime, slowly your H primes become diagonal. And therefore the eigenvalues are all sitting there. And this way we get all of the eigenvalues. Okay. You can, if you just want the biggest one, go for the power method. It's very quick on a tridiagonal matrix. And also on a tridiagonal matrix, you could go back to the first thing you were taught about finding eigenvalues, which is to use the characteristic equation, the determinant of A minus lambda I. On the whole, you should never ever do this, but the determinant of a tridiagonal matrix is only n operations. Okay. I still don't like root solving on this. This is very good. So this would be hideous to program, but you'll not program any of this. So remember, you must not program any of this. There are these professionally written, safe, free, everything nice, accurate, fast packages. Use them, please. Okay.